Download this code from codegive.com, link in the description below. OK, let's dive deep into debugging broken code specifically on the x64 platform, addressing potential issues and providing a comprehensive guide with code examples. We'll cover areas relevant to both older, 16.7, and newer, 16.8 plus, versions of Visual Studio, or related environments. Introduction. Debugging x64 code can be tricky because of differences in the calling convention, memory layout, and register usage compared to x86, 32-bit, code. The 64-bit environment offers increased address space but can introduce new types of bugs, often related to pointer size, typecasting, and memory alignment. Key areas of focus. *x64 calling convention * how arguments are passed to functions, what registers are used for return values, and how the stack is managed. Pointer size and typecasting * the fact that pointers are 64 bits wide and the implications for converting between different types. Memory alignment * data structures and variables must be properly aligned in memory to avoid performance penalties or even crashes. Register usage * understanding which registers are volatile, caller saved, and non-volatile, CALI saved, and how they impact debugging. Stack management * ensuring correct stack frame setup and teardown to prevent stack corruption. Common x64 specific bugs * address range errors, bit manipulation problems, and issues with interop between 32-bit and 64-bit code. Debugging tools and techniques * using Visual Studio's debugger effectively, including breakpoints, watch windows, the disassembly view, and memory examination. Error handling * properly handling errors, exceptions, and unexpected behaviors in x64 environment. 1. x64 calling convention, Windows. The x64 calling convention on Windows, also known as the Microsoft x64 calling convention, is crucial to understand when debugging. Here's a summary. Argument passing * the first four integer or pointer arguments are passed in registers. RCX * first argument. RDX * second argument. R8 * third argument. R9 * fourth argument. Floating point arguments are passed in XMM0, XMM1, XMM2, and XMM3. Any remaining arguments are pushed onto the stack, right to left. Return value * the return value is passed in racks for integer / pointer types and XMM0 for floating point types. Shadow space * the caller reserves 32 bytes of shadow space on the stack for the first four arguments, even if those arguments are passed in registers. This space is used by the CALI to store these registers if needed. Non-volatile registers * these registers must be preserved by the CALI. RBX, RBP, RDI, RSI, RSP, R12, R13, R14, R15. Volatile registers * these registers can be modified by the CALI without needing to be saved. Racks, RCX, RDX, R8, R9, R10, R11. Stack alignment * the stack pointer, RSP, must be aligned to a 16-byte boundary before a call instruction. Example, illustrating calling convention and potential bug. Debugging scenario * 1. Set a breakpoint * set a breakpoint inside my function, at the int sum equals, line. 2. Examine registers * when the breakpoint hits, open the registers window in Visual Studio, debug -windows-registers. 3. Verify register values *. Check the values of RCX, RDX, R8, and R9. They should correspond to the first 4 arguments, 1, 2, 3, 4. 4. Examine stack *. Examine the stack memory. You'll see the shadow space and, further down, the value of E5. Potential bug and how to find it *. Suppose we made a mistake and forgot to add E in the my function. When you run the code, you'll get an incorrect result. By stepping through the code in the debugger, you'll observe that the sum variable only contains the sum of the first 4 arguments and doesn't include E. You can use watch windows for sum, A, B, C, D, and E. 2. Pointer size and typecasting. In x64, pointers are 64 bits, 8 bytes, wide. This has important implications for typecasting and pointer arithmetic. Example, illustrating pointer size and potential bug. Debugging scenario *. 1. Set a breakpoint *. Set a breakpoint before and after the typecast to uint32_t. 2. Examine variables *. In the debugger, inspect the value of ptr and ptr as int. You'll see that ptr is a 64-bit address, while ptr as int is a 32-bit value, and the upper 32 bits of the address have been discarded. Potential bug and how to find it *. The example shows that casting a 64-bit pointer to a 32-bit integer type truncates the address. If you then try to cast the 32-bit integer back to a pointer and dereference it, you'll likely access an invalid memory location, leading to a crash or unpredictable behavior. How to debug *. Run the code in debug mode. You'll see that bad ptr will be a different address from the original pointer. If you uncomment the line to dereference the bad ptr, you will get an exception, and the debugger will show you the exact location of memory access violation. 3. Memory alignment. x64 processors can access memory more efficiently when data is aligned to its natural size. For example, *int should be aligned to a 4-byte boundary. *double should be aligned to an 8-byte boundary. *pointers should be aligned to an 8-byte boundary, x64. Misaligned memory access can lead to performance penalties or, in some cases, exceptions, especially on certain architectures. Example, illustrating alignment issues. Debugging scenario *. 1. Examine memory layout *. Use the debugger to examine the memory layout of the myStruct object. You'll see that the members are packed tightly together without any padding. 2. Set breakpoints *. Set breakpoints before and after accessing s.b and s.d. 3. Observe performance. If possible, while it's hard to measure directly, misaligned access can sometimes be noticeable in performance-critical code. Potential bug and how to find it *. The pragma pack directive forces the compiler to pack the structure tightly, removing any padding that would normally be added for alignment. In this example, the int b and double d members are likely to be misaligned. This can cause performance degradation, and in rare cases, it might lead to exceptions on some platforms. The size of the struct shows if there is alignment. If there is no pragma pack, the size would have been 24. 4. Register usage. Understanding register usage is critical when examining assembly code during debugging. Refer to the x64 calling convention above to understand which registers are volatile, caller saved, and non-volatile, CALI saved. Example, illustrating register usage and potential bug. Debugging scenario *. 1. Disassembly view *. Open the disassembly view, debug-windows-disassembly. 2. Set breakpoints * set breakpoints inside my function, before and after the multiplication. 3. Examine registers * when the breakpoint hits, examine the values of RCX, input argument X, RAX, intermediate result and return value, and any other registers used in the calculation. Potential bug and how to find it *. Suppose there is another function calling my function in a loop and not handling the RAX result, you will notice incorrect results on the screen. The compiler can use volatile registers to do other tasks that impact the final output. 5. Stack management. Incorrect stack management is a common source of errors, especially when dealing with function calls, local variables, and exception handling. Example, illustrating stack overflow. Debugging scenario * 1. Run the code * run the code. You will likely encounter a stack overflow exception. 2. Examine the call stack * in Visual Studio, open the call stack window, debug -windows -call stack. You'll see a long sequence of calls to recursive function, indicating that the recursion is not terminating correctly or is consuming too much stack space. Potential bug and how to find it *. In this example, the large array ARR allocated on the stack within each call to recursive function quickly consumes the available stack space, leading to a stack overflow. The debugger will show the stack overflow exception and the call stack, allowing you to identify the recursive function as the source of the problem. 6. Common x64 specific bugs. Address range errors accidental use of 32-bit variables to store 64-bit addresses. Bit manipulation errors incorrect bit shifting or masking operations due to the larger word size. Interop issues, 32-bit / 64-bit incorrect data marshalling when calling between 32-bit and 64-bit modules. Ensure that you are using the same bitness when combining components. Integer overflow large integer can exceed 32-bit on x86 platform, but still under 64-bit integer. Debugging on x64 platform will hide such bugs. 7. Debugging tools and techniques, Visual Studio. Breakpoints set breakpoints at strategic locations in your code to pause execution and examine variables, registers, and memory. Watch windows add variables and expressions to the watch window to monitor their values as you step through the code. Locals window the locals window automatically displays the values of variables in the current scope. Autos window the autos window displays variables that are used on the current line and the previous line of code. Disassembly view view the generated assembly code to understand how your C++ code is being compiled and executed. Useful for understanding calling conventions, register usage, and optimization. Memory window examine raw memory contents at specific addresses. Useful for inspecting data structures and memory layouts. Call stack window view the call stack to trace the sequence of function calls that led to the current point of execution. Conditional breakpoints set breakpoints that only trigger when a specific condition is met. Data breakpoints set breakpoints that trigger when a specific memory location is accessed. Sometimes called watch points. Performance profiler use the profiler to identify performance bottlenecks in your code. 8. Error handling. In x64, exception handling is typically done using SEH, structured exception handling, on Windows. It's important to ensure that your code handles exceptions gracefully to prevent crashes and provide meaningful error messages. Example, illustrating exception handling. Debugging scenario *. 1. Set a breakpoint * set a breakpoint inside the catch block. 2. Run the code * run the code. The exception will be caught, and the breakpoint will be hit. 3. Examine exception information * in Visual Studio. You can examine the exception information to understand the type of exception that occurred and the location where it was thrown. Potential bug and how to find it *. The example demonstrates a simple null pointer dereference, which will cause an exception. Proper exception handling allows you to catch the exception and prevent the program from crashing. The debugger helps you identify the location of the exception and examine the state of the program at the time of the exception. Visual Studio version 16.7 vs 16.8+. While the core debugging principles remain the same, there may be subtle differences and improvements in the debugging tools and experience between Visual Studio 16.7 and 16.8+. Some potential areas of difference include performance improvements * newer versions of Visual Studio often have performance improvements in the debugger, making debugging large or complex applications faster. Enhanced visualizations * Visual Studio might add improved visualizations for memory, registers, or data structures in newer versions. Bug fixes * bugs and stability issues in the debugger are often fixed in newer versions. New features * new debugging features might be introduced in newer versions. Check the Visual Studio release notes for details. Compiler optimizations * the compiler in newer versions may produce different assembly code than the compiler in older versions. This can sometimes affect how you debug your code. C++ language standard * if you are using a different C++ standard in the two versions, it may cause different compiling results and the way to debug your code. Troubleshooting tips. Enable debug information * ensure that your code is compiled with debug information enabled, usually the /zi or /zi compiler flags in Visual Studio. This allows the debugger to map assembly code back to your source code, making debugging much easier. Use a debug build * always debug a debug build, rather than a release build, of your code. Release builds are typically optimized for performance, which can make debugging more difficult. Simplify the problem * if you're debugging a complex issue, try to simplify the problem by creating a minimal reproducible example. This can help you isolate the source of the bug. Use logging * add logging statements to your code to help you track the flow of execution and identify potential problems. Consult documentation * refer to the Visual Studio documentation, the Intel or AMD architecture manuals, and other relevant resources for detailed information on debugging x64 code. Google search * search online for error messages, debugging techniques, and solutions to common problems. Conclusion. Debugging x64 code requires a solid understanding of the x64 architecture, the calling convention, and potential sources of bugs. By using the debugging tools effectively and following the techniques outlined in this guide, you can effectively debug your x64 applications and resolve challenging issues. Remember to pay close attention to memory management, pointer sizes, alignment, and register usage to avoid common pitfalls. Also, keep your Visual Studio updated. This comprehensive guide provides a strong foundation for debugging x64 code. Remember to adapt these techniques to your specific debugging scenarios and to consult relevant documentation and resources as needed. Good luck.